In this video, I'd like to cover what I think is one of the most important tools that you can have while solving integrals, and that tool is integration by parts. And I kind of like to think of it as a product rule for integration. So if it's a product rule, a good starting point would be the product rule for derivatives, which is that the derivative of f of x times g of x is the derivative of f of x times g of x plus f of x times the derivative of g of x. Now, since we're doing integration, why don't we try to integrate both sides? So we'll take the definite integral from a to b of both sides, and obviously since integration is a linear operator, we can split this up into two integrals right here. And now from the fundamental theorem of calculus, we know that this integral and derivative are going to cancel off, and this is just going to be our two functions evaluated at the endpoints. And sometimes this is known as Leibniz rule. Now we can substitute this into the previous equation to get this right here. Now what we're going to do is we're actually going to rearrange. Now we can actually rearrange this equation by subtracting the integral from a to b of the derivative of f of x dx multiplied by g of x from both sides. And so we're going to end up with this equation right here, which is the general formula for integration by parts. Now sometimes you'll hear of these being called your boundary terms. Now if we're dealing with an indefinite integral, we don't have to worry about the endpoints, and this equation simplifies to what we see here. Now most commonly you're going to see it written in this notation, which is that the integral of u dv is equal to u times v subtract the integral of v du, where obviously we've said that u is f of x and du is df of x dx times dx, etc. So where is it useful? Well, we use integration by parts to evaluate integrals that are composed of products of functions. Our goal is obviously to identify two functions, u and dv, whose product make up the integral. And once we have found u and dv, we need to find the derivative of u and an antiderivative of dv. And this gives us du and v, which we can then plug into this this formula right here, which will allow us to solve the integral. Now, the problem that people have when they first start to learn integration by parts is that they aren't really sure which function should be u and which function should be dv. So what we really want is we want du to either vanish. In that case, this integral would become 0, and this integral here would simply just be the product of u and v. But usually that's not what's going to happen. So the next best thing would to have du cancel out a few things from v when they're multiplied together. Now, one way of choosing u is called the LIATE rule. And so here this L stands for logarithmic functions. And so those are your first go-to choice. If you see a logarithmic function in your integral, chances are that is your best option for choosing u. And the reason is, say we think of ln of x, when we take the derivative of that, we are going to get 1 over x. And so say we have a polynomial function as our dv. When we integrate that, we're going to get another polynomial, and if we multiply it by du, we're going to be simply canceling off an x from every term involving an x, and obviously that's going to be pretty easy to integrate. Next is inverse trigonometric, and the reason why that is desirable for u is that when you take the derivative of an inverse trigonometric function, you're going to get some sort of algebraic function, and as you keep taking further derivatives, you'll just be getting more and more algebraic functions. Which leads me into A, which stands for algebraic functions. Now, in the case that you have a polynomial, it's really nice because as you take derivatives of your polynomial, eventually you're going to get down to either a constant or 0, depending on how many times you have to apply your integration by parts. Next is your trigonometric functions, and the reason why you don't really want to choose these as your u unless you absolutely need to is because as you take a derivative of a trigonometric function, it just kind of keeps cycling. Like if you take the derivative of sine, you're going to get cosine. Then when you take another derivative of that, you're going to be straight back to negative sine. And so it would just require you to take a bunch of, you'd have to keep reapplying integration by parts because you're not getting anything that'll cancel out. And finally, your worst choice for u would be exponential functions, and that's simply because when you take a derivative of an exponential, nothing happens. It spits out the function that you just took a derivative of. So in part 2, I'll show you some examples that you would commonly see in a Calc 2 course, and I'd also like to show you some examples that are more abstract, like I've got one that I like anyway from quantum mechanics, and I'd just like to show you why integration by parts is such an important tool, and it isn't something that you should ever forget about if you ever plan on taking more advanced mathematics and physics courses.